Here we have one of the most pedestrian and ubiquitous input devices out there, the keyboard. And what's interesting about the keyboard is that there's actually an enormous amount that happens between when I type with my fingers and when something appears on the screen. Through the magic of direct manipulation, it looks like with a key press to the screen appearance, it's instant. But what are all the intermediate steps? That's what we're going to go through in today's video. If you take an everyday keyboard like the one that you see in the image here, and you peel it back, you get something that looks like this. It's not just a cool wallpaper pattern. What we see in this layer here is a circuit that's able to ascertain which key or keys have been pressed at an impressively low cost. So if we take all of these keys and we pop this open, what we'll see under the hood is that we got a lot of rows and we've got a lot of columns. So these are the wires that we saw inside the keyboard. So we have our rows, and we have the columns here. So altogether, we might have 8 or 9 rows. We might have a dozen columns. It'll depend, obviously, on the exact keyboard layout. What's notable about this, though, is that you have many more keys on your keyboard than there are rows plus columns. So how do we take, 8 or 9 rows, 10 or 11 columns? These are going to go together to an encoder that sits over here and listens to all of these wires. But again, there are more keys than there are wires. So how does this all add up together? If we zoom in, what you see here is that each key represents the intersection of a row and a column. When the key is up, all of these switches, each key is a switch, the circuits are open, they're not closed. When we press down, that will complete a circuit for a particular column and for a particular row. So if I press down this key here, which might be A, both this column is going to light up and this row is going to light up. And so this is like if you played the board game Battleship, where you call out coordinates in row column space. Same idea here. The encoder is going to see column 1 is hot and row 3 is hot. The keyboard encoder knows that when column 1 is hot and row 3 is hot, that corresponds to a particular physical key on the keyboard. Any individual keyboard could be labeled with lots of different languages, do lots of different stuff. So what we see with the key codes that the encoder talks about, those are the physical keys, not yet the alphabet that will appear on the screen. So in addition to A through Z and 0 through 9, we've got all of your F keys, all the other stuff. The keyboard I showed you here has a number keypad on the right. The key code for that number 1 on the right is different than the key code for the number 1 on the top left of the keyboard. So far, what we've done is we've taken the physical press of your finger, we've used that to close a circuit, and we've used that to describe a key code. Now we're going to talk about how that key code bubbles up. Your encoder is going to send to the computer the key code that is pressed. So if I've got my computer right here, it's going to hear from the keyboard 1C, which might be the key code for A. From there, that might be interpreted by the computer to understand that on a US layout keyboard, That's what 1C means, and then that's what we'll see on the screen. This skips all of the graphics processing part of it, but for today, we're just talking about how the input side of things work. So let's say we have a different example. Let's say that you press, column 3, row 4 here, which might correspond to maybe C, and that will have its different corresponding key code, and then that's going to light up a different row and column. More interestingly, what happens if while key A is pressed, you also press S, which might be in the same row, but a different column? Here, when I press on the S, the encoder is seeing what it saw before, column 1, row 3 for A, and now it's also seeing column 2, row 3. If both column 1, row 3 and column 2, row 3 are showing up, then we know that both the A and the S are pressed simultaneously. For the devious among you, because the row and column set here is a little bit underspecified, it is theoretically possible that if you pressed two keys that were ambiguous, two corners here, at exactly the same time, your encoder might not know whether it was this corner pressed or that corner pressed. In reality, few users are that devious, or at least their timing isn't that perfect, and so the encoder is able to tell which key is pressed. We talked a little bit in our history about the role of Grace Hopper in computing and her invention of the compiler. One thing you might notice is that she is an early user of having a keyboard to do programming input, as opposed to punch cards or wires or something that is much lower level. At the time, this was a real advance, but in the intervening decades, we've been able to do a lot better. But the real challenge is that for a lot of the tasks that we want to be able to specify to each other, for example, this diagram I've just drawn here, it can be difficult to shoehorn that purely into things that you could express with a keyboard. If I had to use a keyboard to draw this diagram, it would be pretty slow. So what we're going to do, as we've talked about at several places in this class, is that the big idea of direct manipulation is that you get input directly on top of output. And this is where Doug Engelbart and team in the early 1960s, when they invented the mouse, this was the great leap forward. Well, let's flip that mouse upside down and see what's underneath there. What you'll see, and this is kind of cool, in this early mouse, what we have are two different wheels. These are, in fact, variable resistors. So the way that we're going to encode the position of the mouse is we have one wheel, a variable resistor, also called a potentiometer, that's going to encode our x direction, and a separate wheel that's going to encode our y direction. This is pretty good, except that there will be a limit when we turn this wheel. The resistor will turn, and then it stops, and then you need to go back. After a few decades of innovation, and again we can pop the hood on this, we can see how things have evolved significantly. This is a commodity mouse, and what I'd like to use it as an example of is not necessarily how your computer today works. Of course, if you have a tablet or you're using a trackpad, things may be different. What I want to use this as an example of is a way that you can take an analog signal like you get from a mouse and in a low-cost, high-robustness way, convert that into a digital signal. So that gray ball there is the trackball for the mouse. How does that get converted into something digital? Well, if you look at it, you'll see that, again, there is a wheel, just like in the early mouse. And this wheel has solid parts and transparent parts. That enables an infrared detector, if you shine a light through this wheel, to see whether it's over a solid part or a transparent part. This is the basis for what's known as a rotary encoder. Rotary encoders are widely used throughout mechanical systems that need closed-loop feedback. It takes what used to be analog, and in a discrete sense, it now makes it digital. You can either see through the wheel or you can't. 1 and 0, high and low. So we roll the wheel forward, we go from transparent to opaque. Okay, high to low, good. Let's say we roll it backward. We go from opaque to transparent. But did we roll it forward or did we roll it backward? In the basic version, you can't tell. So now we're going to get a little bit fancier, and we're going to add an offset encoder. This way, if we see a particular pattern, we go from high, high to low, high, we know we're going in one direction. By contrast, if we go the other way, we go from low, high to high, high, we're going in the other direction. Holy cow, now we have the ability, both in X and in Y, to be able to take our analog motions on a surface and turn those into digital movements. That lets us now control a pointer on a screen. If you think about a capacitive touch sensor like you might have in your smartphone or tablet, or other sensing input devices that you may be using, the details of this will vary somewhat, but the principle that there is a structured grid of electrical systems with an encoder of some kind, it could be through a rotary encoding wheel like this, or the encoder that we talked about on the keyboard, that's taking your analog motions, your physical presses, your physical movements, and turning those into something digital that can then get sent across the wire to a computer, which lets you move your mouse and type the keyboard. That's what we've seen is now possible today.